Right, today we're going to be covering the Physics Paper 2, this is a multiple choice extended paper, and the code for this is 0625/21. So it's variant 1, and this is for October-November 2018. This is the Cambridge International Examinations, Cambridge IGCSE. Alright, let's begin.
Let's start her up.
Yeah.
Question 1. The diagram shows part of a micrometer screw gauge. What is the smallest reading that can be achieved using this micrometer screw gauge? Now a micrometer screw gauge will read 1/100th of a millimeter, which means the smallest reading is B, 0.01 millimeters. Question 2. A small light ball is dropped from the top of a tall building. Which graph shows how the speed of the ball changes with time? Let's look at the key points. It's a small ball, it's a light ball, that's actually a very important bit there, and it's a tall building. So it's basically telling us it's going to reach a terminal velocity. So there we go. So it would do A in a vacuum. B, I'm not sure why that would ever happen. D starts off with a high speed and slows down. That'd be like something coming in from space, or something where the power to push it forward is reduced. And C, there we go, starts off accelerating and slows down to a constant speed, which is what's going to happen for terminal velocity. So the answer is C. 3. A runner runs 300 meters at an average speed of 3 meters per second. She then runs another 300 meters at an average speed of 6 meters per second. What is her average speed for the total distance of 600 meters? Okay, well, what do we know? We know that average speed is total distance divided by total time. Now, if we look at the question, we have the total distance. What we don't have is the total time. So we need to calculate the time for each section. So we get time 1 is going to be 300 meters divided by 3 meters per second, which is 100 seconds. Time 2 will be the remaining 300 meters divided by 6 meters per second, which will give us a time taken of 50 seconds. So the total time is 100 plus 50 seconds is 150 seconds. So the average speed can now be calculated. The total distance, 600 meters, divided by 150 seconds, will give us 4 meters per second, which is option B. Question 4. A helium balloon is tied to a top pan balance. The metal block of mass 100 grams is placed on the balance. The reading on the balance is then 91 grams. Which statement can be deduced from this experiment? The balloon exerts a downward force of 0.09 newtons. No, it exerts an upward force. The helium has a mass of -9 grams. No, that's just how it's reading it. C, the helium has a mass of +9 grams. No. And D, the resultant downward force on top pan balance is 0.91 newtons. Yeah. Because the force, of course, is from the weight, which is mass times gravity, which in this case is just 91 grams multiplied by 10 meters per second squared, which is 0.091 kilograms times 10 meters per second squared, which is 0.91 newtons. There we are. Question 5. A liquid has a volume of 0.04 meters cubed and a mass of 30,000 grams. What is the density of the liquid? Alright, well, density is mass divided by volume, which in this case is 30 kilograms divided by 0.040 meters cubed. There we go. That's it, and that will give us a density of 750 kilograms per meter cubed, which is option C. 6. A resultant force acts on an object of mass 0.5 kilograms for 3 seconds. What is the change in velocity caused by this force? Okay, so this is a two-parter. Here we go. First we need F equals ma. Force is mass times acceleration, and we want to calculate the acceleration. It's force divided by mass, which is 4.0 newtons, divided by 0.50 kilograms, which will give us a value for the acceleration of 8 meters per second squared. we want our change in velocity. Well, speed equals acceleration times time. So change in velocity will be the acceleration times the change in time. So that will give us 8 meters per second squared times 3 seconds, which is 24 meters per second. Option D. Question 7. Which quantities are both vectors? Let's look at that. Acceleration and force, yes. Acceleration and pressure, no. Density and force, no. Density and pressure, no. So the answer is A. Acceleration and force. Question 8. A moving ball with momentum of 25 kilograms meters per second collides head-on with a wall. It rebounds from the wall with the same speed but in the opposite direction. The time of the collision is 50 milliseconds. What is the average force extended on the wall by the ball during the collision? Okay, so let's look at what's happening. We've got 25 kilograms meters per second. In that direction, after it collides, it comes back with 25 kilograms meters per second in the other direction. So what that means, we'll take one direction as positive, one direction as negative. That would be negative. So the momentum has gone from positive to negative. Well, how does that affect things? Well, first of all, let's look at this. The force is given by the change in momentum divided by the change in time. Now we start with our final momentum, negative 25. I'll just put Newton seconds, it takes up less space, minus our initial momentum, which is 25 Newton seconds, divided by the change in time, which is 50 milliseconds. There we go. And let's rewrite that. That then becomes negative 50 Newton seconds over 50 times 10 to the negative 3 seconds. And that will give us a value of negative 1,000 newtons. Now, all that means is that is the force that the ball experiences. Well, if the ball experiences a force of negative 1,000, the ball experiences a force of 1,000 newtons. And you could just look at it from this point and say, well, you know what, it has to be the one that's 1,000, that would be okay as well. There we go. 9. Which device is designed to convert chemical energy into kinetic energy? Okay, so stuff that's stored into stuff that is moving. An AC generator? No, that creates electrical. Battery powered torch? Nothing moves at the end. A car engine? Yes, that takes petrol and converts it into movement. And a wind up mechanical clock? No, that takes the stored elastic potential energy there. 10. An object initially at rest is dropped from a height of 12 meters. The change in gravitational potential energy when it falls to the ground is 565 joules. The frictional forces are negligible. What is its speed when it hits the ground? Okay, again, we're doing something here where they're trying to give us a bit too much information. You see that there? We don't need it. We don't need it because we need the mass to be able to use it. So what we do is we start off with this situation here. We've got some kind of gravitational potential energy and it's changing into kinetic energy. Well, that's mgh changing into 1/2 mv squared. Now we can cancel the mass on both sides. We divide by mass. Now we can rearrange for v. V squared equals 2gh. V equals the square root of 2gh. And then we can put in the numbers we have. It's the square root of 2 times gravity, which is 10 meters per second squared, times 12.0 meters. There we are. And that will give us a value, square root of 240, which will work out to be about 15.5 meters per second, which is option B. Question 11. A man climbs a ladder. Which two quantities can be used to calculate the useful power of the man? Power is work done divided by time. So we need to find the work done and we need to find the time. That's how we're going to get the power. So the weight of the man and the time taken, well, that tells us the weight. It doesn't tell us how high up he's gone. So we don't know what his work done is. We don't know what his change in gravitational potential energy actually is. So no, it's not enough. The weight of the man and the vertical distance moved only, well, that gives the work done, but no time. C, the work done by the man and time taken only, that would do the job nicely. And D, the work done by the man and vertical distance only, well, we don't know his weight, so we can't calculate the work done. The answer is option C. 12. A manometer is used to measure the pressure of a gas supply. Which change gives a greater value of height h? Right, let's put down what we're actually dealing with here. What the manometer gives us is a change in pressure between two sides, and that change in pressure is given by density times gravity times this change in height. So if we want to, for the same change in pressure, get a bigger change in height, we can't change gravity. We're going to have to change the density and make it smaller. So what are our options? Option A, use a less dense liquid. That would do it. B, more dense. No. C, narrower tube, doesn't change it. And D, wider tube, also doesn't change. Question 13. A wash basin has an exit pipe covered with a plug of area 12 centimeters squared. A chain is attached to the center of the plug to assist in pulling the plug away from the exit hole. The wash basin contains water to a depth of 0.08 meters. The density of the water is 1,000 kilograms per meter cubed. Now, it wants us to calculate the force acting on the plug. Well, if you wanted to, you could quickly look at this and guess it. You could guess it's going to be A. Why? Because this is the weight of a person. That's the weight of 10 people, give or take. And that's the weight of about, 100 people? So, given that we have the capacity to pull a plug out of a wash basin, we'd probably say it's A. But let's just prove that. Let's just run through the calculations. Now, first things first, what we want to do, we're going to combine two things. We're going to want to find the pressure, and then once we have the pressure, we use our equation for pressure equals force over area to find the value of the force. Okay, so first of all, we get pressure in a liquid. Pressure equals density times gravity times height. We want to find the pressure at the bottom, next to the plug. Okay, so the pressure density is 1,000. I won't bother putting in the units at this point. Times gravity, which is 10, times height, 0.080 meters. And that will give us a value of 800 pascals. Now, normally we've got pressure equals force over area when we're dealing with something that's a solid. In this case, we've got the area. So what we're going to do is change that. That gives us force equals pressure times area. Alright, so the force then is given by 800 pascals multiplied by 12 centimeters squared. But pascals, that's a unit part of which is in meters squared. It's newtons per meter squared. This is centimeters squared, so I have to convert that to meters squared. 12 centimeters squared divided by, well, a meter is 100 centimeters times 100 centimeters. So it's 10,000. So it's 12 divided by 10,000 multiplied by 800. And if we put that into the calculator, that will give us a value of 0.96 newtons. There we are. And the answer is option A. Right. Question 14. Diagram 1 shows apparatus being used to observe smoke particles. Diagram 2 shows how a smoke particle moves randomly. Why do the smoke particles move randomly? Well, what happens? Here it's probably just been hit by a small air particle. Here it's been hit by another one. Here another one. So it gets to here, another one. Here another one. And it's not, to be fair, it's not that easy to see when you're looking at it under a microscope. But what's happening is these air molecules are just flowing around, hitting it, and that's why it's changing direction. Okay, so why does it move randomly? Answer A. They're hit by air molecules. Let's look through the other ones. B, they're less dense than air? No. C, they're moved by convection currents. They might be, but these rapid small movements, the ones that we're looking for, they are because of the collisions. D, they gain energy from light. Not enough to move like that. 15. The gas in a sealed container is compressed at constant temperature. Which graph shows how the pressure of the gas changes with volume? Alright, well, what do we know? Let's do a basic little thing. Here we get piston, putting it in. As we push it in, as the volume gets very small, the pressure gets very big. And as the volume gets very big, the pressure gets very small. Let's see what graph does that. Nope, small pressure, small volume. Pressure remains the same. Small pressure, small volume. D, small volume, big pressure. There we go. And big volume, small pressure. 16. The distance between two electricity pylons is 60 metres. An engineer fits a cable of length 62 metres between the pylons. Why does the engineer choose a cable that is longer than the distance between the two pylons? And the answer is, actually, as it gets cold in winter, there is less cable. It's not 62 metres long anymore. It might only be 61 metres long. So it's to allow for contraction in cold weather. And that's actually really important. Otherwise the cables will break, they'll fall over, it gets very dangerous. So let's look at the other options. B is to create a slope in a cable for electrons to flow down. No, that's not how electrons work. C, to keep the current low and the voltage high. Well, depends how high up it is, doesn't it? No, it's not that. D, to reduce magnetic fields around the cable. That doesn't work either. Question 17. The diagram shows a liquid in glass thermometer. Which change increases the sensitivity of the thermometer? Well, a narrower tube would do that. There we are. Wider tube, make it less sensitive. Thicker glass would just alter the time it takes to reach the correct reading, and thinner glass, again, just alters that time. There we are. It doesn't make it more sensitive to small changes. So your small change, let's assume you've got this unlimited amount of time, then for a small change you just want that narrower capillary tube so you can read the small change. Question 18. An object of mass 800 grams and specific heat capacity of 250 joules per kilogram per degree Celsius is heated. It absorbs 5,300 joules of energy. What is the increase in temperature of the object? Wow. Let's put down our equation here. E equals mc delta T. We're being asked for the increase in temperature. Delta T would be rearranging the one above. E divided by mc. So let's put in the numbers. I won't put in the units at the end because they're too big. There's too many of them. I can't squeeze them in this little space to the edge of the screen. Okay, so let's put them in. We've got the energy is 5,300 divided by mass 0.8 kilograms times specific heat capacity of 250. There we go, just squeezed it in. And if we put all that information into our calculator, then we're going to get a value of 26.5 degrees Celsius, which if we round it up is 27. Question 19. On a cold day, a shiny metal rod feels colder to the touch than a black plastic rod. Which statement explains this observation? A metal rod's a better absorber of infrared radiation? Nope. Metal rod's a better thermal conductor? Yeah. What's happening here is it's taking the heat away from your hand to heat itself up. C, the metal rod's a worse absorber. Again, been told nothing about the amount of sunshine or sunlight it's been exposed to. D, the metal rod is a worse thermal conductor than a plastic rod. No, that would make it feel warmer on the cold day. Question 20. One end of a copper bar is heated to a high temperature. Which mechanism is responsible for the transfer of thermal energy to the other end of the copper bar? Well, this happens in two ways. It happens because you've got all this sea of electrons which are able to transfer the heat across, but also you've got all these lattice ions that are vibrating and carrying that vibration across. Okay, so let's see what our options are. A, vibration of copper ions only. It's definitely not that, because the electrons play a very important role, and that's why metals. One of the reasons why metals are such good conductors. The lattice vibrations of copper ions and the movement of high energy electrons along the bar. Yeah, they get high energy, they're bouncing around, that passes on, that would work. C, the movement of high energy copper ions? No, they don't move very much. And D, the movement of high energy electrons along the bar only. No, it's a mixture of both of them. There we are. Option B. Question 21. Plane water waves travel from a shallow region to a deeper region. They travel more quickly in the deeper region. Which diagram shows the wave patterns? Alright, well, let's look at that. They're travelling more quickly, then they're going to move away. Like that. That's what's happening. And the picture that most closely resembles that is option C. Question 22. Which statement about the image formed by a plane mirror is correct? The image is larger than the object? Nope. Nope, it's the same size, so it's not smaller, it's not larger. The image is twice as far from the mirror as the object? No. And D, the image is virtual. Yeah, it's not a real image. There we go, it's a virtual image. Question 23. A ray of light is incident on a glass air surface. The diagram shows the ray of light at different angles of incidences in the glass. What is the refractive index of the glass? Now, if we look at the centre section here, what we can see is that this is our critical angle. And straight away from that, we can put that into our equation. N equals 1 over sine of C, where C here is the critical angle. So we can use that to calculate the value for the refractive index. So it's 1 divided by the sine of 44 degrees. And when you put this into your calculator, make sure that your calculator is in degrees. Okay, very important that, because often if you're doing maths, you'll have to convert it to radians and back again. So make sure your calculator is in degrees when you're doing this. And that should give you a nice value. There we go, of 1.44. Question 24. Different parts of the electromagnetic spectrum are used for different purposes. Below are 4 statements about parts of the spectrum. So let's look at them. Statement 1. Infrared waves are used in television remote controls. Yes, they are. Statement 2. Radio waves are used to transmit television pictures. No. UV waves are used for intruder alarms. No. And 4. X-rays are used for security checks. Absolutely true. Alright, so which statements are correct? Looking at the things above, 1 and 4, so that is option B. Question 25. Iron is used for the core of a transformer and steel is used to make a bar magnet. Which statement explains the uses of iron and steel? Well, very quickly, let's just review it. Iron loses its magnetism at room temperature. It only has it when it's in an external magnetic field. That's why it's so good with alternating currents and in a transformer. Steel is used to make a bar magnet because it holds its magnetic field. So, iron's a permanent magnet? No, it's not the first one. B, iron's a permanent magnetic material? No, still not that one. There we go. C, iron's a temporary magnetic material? Yes. And steel is a permanent magnetic material? Yes. And D, iron is non-magnetic? No, it becomes magnetic in a magnetic field. There we go. So, the answer is C. 26. A sheet of ice floats on water. A source of sound, S, is positioned at the edge of the ice sheet. 4 microphones are placed equal distances from S. Which microphone detects the sound from S first? Okay, let's look at this. What we want is the speed of sound in air. Well, that is about 340 meters per second. Let's look at the speed of sound in water, or a liquid actually. There we go. Generally, in a liquid, we're looking about 1 kilometer a second, and in a solid, so I should really have liquid at that bit there. There we go. Speed of sound in a solid is about 5 kilometers a second. So which microphone will hear it first? It'll be the microphone that's on the same solid as the sound source. 27. A bar magnet is placed inside a current carrying coil. The diagram shows 4 different experiments. Here we've got the magnet being slowly removed, here we've got the magnet being slowly removed, but it's a direct current. We get alternating currents on the left and direct currents on the right. Which experiment demagnetizes the magnet? Okay, well, let's look at this. The magnet will not be demagnetized by the direct current because it's not changing the magnetism, it's not reducing it. One will reduce the magnetic field while at the same time alternating it all the time. That will demagnetize the magnet. And the same thing happens in 3. The magnetic field of the material will change direction again and again and again, and it gets reduced, so it changes and becomes less and less powerful. So 1 and 3. 28. The diagram represents two different electric fields. A single electron is located in each of the fields. Which row gives a correct direction of the force on the electron and the field in which there is a larger force on it? Alright, as with all things electricity, these arrows represent the direction of force on a positive charge. So a negative charge will experience a force downwards. So the electrons will experience a force downwards. So that's A or B. Now in terms of which one has the larger force, field 1 has the larger magnetic field strength because these lines are closer together. So the larger field will be field 1, and the answer is option A. Question 29. The resistance of a component in a circuit is found using an ammeter and a voltmeter. How are the ammeter and voltmeter connected? Well, the voltmeter should be in parallel and the ammeter should be in series. There we are, and that is option C. Question 30. The table gives data for 4 different electrical devices. Which device develops the greatest power? Alright, well, power equals current times voltage. Alright, so if we take the values of current and the values of voltage, we multiply them together, what we will get is the power. So that's 36 watts, 44 watts, 40 watts, and 48 watts. So the device that develops the greatest power is the mains lamp, which is option D. Question 31. The circuit diagram shows a fixed resistor R and a thermistor T used in a potential divider circuit. VR and VT are the potential differences across R and T, respectively. What happens to VR and VT as the temperature of the resistor decreases? Right, let's look at what happens as the temperature decreases. Well, as the temperature decreases, the resistance of the thermistor increases. The voltage across the thermistor will increase, and because of that, the voltage across the resistor will decrease. So as the voltage across the thermistor increases, the voltage across the resistor decreases, and that's because the voltage across the thermistor plus the voltage across the resistor is equal to the supply voltage. There we go. Alright, so let's look at that. The voltage across the thermistor, we know that increases. Let's highlight those two. And the voltage across the resistor decreases. So the answer is option A. Question 32. The circuit diagram shows a power supply connected to some circuit components. In the diagram, P and Q are the terminals of the DC power supply. Okay. Under which circumstances does the ammeter show a reading other than 0? Alright, well the ammeter will show a reading other than 0 when there's a current travelling through it, and that will happen when there's a current travelling in this direction. Now, when we say when there's a current travelling in this direction, what we're talking about here is conventional current. Why in that direction? Why not the other direction? Because it has to be in agreement with this diode here. So it has to move in the same direction as the diode will allow it to. So that means that this side here would have to be positive and this side here negative, because we're dealing with conventional current, which is the idea that it's the positive charges that move, even though they don't. And that's just left up from hundreds of years ago when they had to guess what it was that was moving, and they guessed positive charges, and they were wrong. But we still use a lot of the conventions from them. So when P is positive and Q is negative, we will see a current, we will see a reading on the ammeter which is not equal to 0. So only when P is positive. There we are. Question 33. The diagram shows a digital circuit with 2 inputs and 1 output. And what describes the action of the circuit? So first of all, let's do a little truth table. Input 1 and 2, and of course our output. Now let's put in all the possible options. We've got 0, 0, 1, 1, 0, 1, 0, 1. There we are. And we'll just put that up and follow it through and create the output table. Then we'll look at the values of the output to see what that represents in terms of one of these options, and, NAND, NOR, or OR. Okay, so first of all, we'll start off with 0, 0, 0, and 0. As we'll follow the top path circuit first, the 0 comes through a NOT gate, that becomes a 1. 0 comes through a NOT gate, becomes a 1. Both travelling through an AND gate, the AND gate will give out a 1 if both inputs are 1. Now, following the bottom path, input 2 is 0, so that's 0, and it becomes a 1 through the NOT gate, so then our final AND gate has 2 inputs that are 1, the output will be 1. There we go. Now let's change that, of course, so input 2 is now equal to 1. So if I put a 1 down here, then that's going to become a 0 and a 0, which means that this will become a 0, and the output will be a 0 as well. There we go, 2 low inputs would give us a 0 output for the final AND gate. So let's change the input, so input 1 is 1 and input 2 is 0. As we follow this through, it becomes 0 on the top. The output from the AND gate with the input of 0 would be a 1 over here as well. This AND gate would give us a 0, so we'd have a 1 and a 0 going into an AND gate, that will give us a 0 also. Now let's change it so both inputs are 1. As they travel through the NOT gates, they will switch to being the opposite, so they both become 0. The output of the AND gate is 0, and on the bottom NOT gate 0, we get 2 zeros going into an AND gate, that will give us a 0 output. There we are, so our output is 1, 0, 0, 0. So it's only high if both of the inputs are low or equal to 0. Now that is pretty much the opposite of an OR gate. So if I put an OR gate in here, what I would expect to have 0, and the output of an OR gate is high if either of the inputs or both is high. So I'd expect 0, 1, 1, 1. It's the opposite of an OR gate, which is an OR gate. And that is option C. There we are. Question 34. Either a fuse or a circuit breaker can be used to protect electrical cables from large currents that could cause overheating. When a fuse is connected, where should it be connected? And when a circuit breaker is connected, where should it be connected? Right, well, both the fuse and the circuit breaker should be connected in the live wire really as early as possible. We're protecting the electrical cables from large currents, so we want to have it as early as possible so that we don't damage the wires in the house, the cables in the house. Okay, so both of them should be as early as possible, both of them should be in the live wire, and both of them should be at point X. So that is option A. Question 35. There is a current of 3 amps in a conductor. The current is changed to 6 amps in the opposite direction. What effect does this have on the magnetic field around the conductor? Well, if you change the direction of the current, you're going to change the direction of the magnetic field. And if you increase the current, you're going to increase the strength of the magnetic field. So we're looking really for those as options. So, A, it decreases, no. B, it decreases, no. C, it increases and acts in the opposite direction, yeah, that looks good. And D, it increases and acts in the same direction, no. Change the direction of the current, change the direction of the magnetic field. So the answer is option C. 36. A wire is placed in a strong magnetic field. When a current is passed through the wire, it moves upwards as shown. Right. The current is reversed. Which direction does the wire now move? The opposite is going to move downwards. So the answer is A. And the reason for that, of course, is because the magnetic field of the wire has been reversed, so it will make the opposite movement. Question 37. Which diagram represents the structure of a neutral atom? So we're looking at the same number of positive charges in the middle as there are negative charges outside. So it's not A, B looks good, not C, and not D. So the answer is B. 2 positive charges in the centre, 2 negative charges outside. Question 38. When a uranium-235 nucleus absorbs a neutron, it becomes unstable and undergoes fission. The fission process produces a barium nucleus, a krypton nucleus, and 3 neutrons. The fission process is represented by the nuclear equation shown below. Which symbol represents the resulting krypton nucleus? Okay, let's look at this. The numbers at the top and the numbers at the bottom have to balance. So let's look at that. 1 plus 235 on the left hand side will have to be equal to 144 plus whatever value we expect for the krypton nucleus, which is protons plus neutrons. We'll just call it the mass number. There we are. Plus 3 lots of the neutrons, 3 neutrons there, so that's 3. So now what we need to do is take 236 minus 144 minus 3, and that will give us the value for M. And that gives us a value of 89. And straight away, actually, there's only one possible answer that it could be, but we can do it that way. Let's fill in the bottom number, because the numbers at the top have to balance. The numbers at the bottom, the charge numbers, also have to balance. So 0 plus 92 should be equal to 56 plus the proton number of the krypton nucleus plus 0. So the proton number will be equal to 92 minus 56. And that gives us a value of 36. So there we are. The answer is A. Excellent. Question 39. The diagram shows the paths of 3 different types of radiation, X, Y, and Z. Which row correctly identifies them? Okay, well, let's identify them ourselves first. Y stops at the first thing it comes across, a tiny bit of plastic, so it's an alpha particle. X is stopped by a few millimeters of aluminium, so that's a beta particle. And gamma goes all the way through everything until it hits some lead, and that means that Z is gamma. Now, let's find the row that identifies that. So we're looking for beta, alpha, gamma, and that is option B. There we are. Question 40. A scientist measures the count rate of a radioactive sample in a laboratory over a period of 12 weeks. The background radiation count rate in the laboratory remains constant at 20 counts per minute. A table shows the scientist's results before the background radiation count is taken into account. Now, in which range does the half-life of the isotope lie? Well, let's just do the count rate with or without the background radiation. So we take 20 away from everything. That will give us 80, 60, 45, 34, 25, 19, and 14. Okay. So now if we look in terms of half-lives, we start with 80. So let's do a little table up here. Number of half-lives and count rate. So we start off with 80, that's 0 half-lives. We go to 40, that would be 1 half-life. We go to 20, that would be 2 half-lives. Now if we look here, 19 is very close to 20. Started with 80, got very close to 20 down here, and that's over a period of 10 weeks. So 10 weeks is close to 2 half-lives. That means that 1 half-life is close to 5 weeks. There we are. We don't really have any more specific information than that. It's about 5 weeks. And that's as good as we're going to get. So let's look at our range. A, between 4 and 6 weeks for a half-life. Yep, that's quite possible. B, 6 and 8. Nope. 8 and 10 and more than 12. No. So the answer is A. Between 4 and 6 weeks, we know the half-life is close to 5 weeks. Alright, excellent. Good job. So hopefully you enjoyed that and that was helpful. If it was, please feel free to like and subscribe. And yeah, have a great day.